Hello, my friends. Thank you for watching this lecture, Uniform Cause Search. In the previous lectures, we learned about different branches of AI. We learned about problem solving by search. We learned about uninformed search. And the last algorithm that we are going to study is Uniform Cause Search, or UCS. This UCS, Uniform Cause Search, this is an algorithm that has been designed for traversing a weighted tree or graph. What is the meaning of weighted? So in graphs, we have unweighted. It means when you want to move from this A to B is the same as moving B to C, or from here, you can go if this is D. So going from A to B and C is the same as going to A to D and C. However, in the case of weighted graphs, we have a weight for each edge, right? So if this is A, B, C, and D, we have some weight here, right? So it means if we go from A to B, the weight is 2. Then from B to D, it's 1. So 2 plus 1 is 3. But if you go from A to C, is 3, and 2 is 5, right? So this weight can be distance between cities, can be the amount of energy from moving one state to another state. So the main goal of UCS is to find the path from one initial state to the goal state with lowest cumulative cost. This is the main objective. Unlike the BFS and DFS, UCS make its decisions based on the total path cost from the root node, right? So from where we start, for example, the total is 2 plus 1, 3, right? And here 3 plus 2, 5. So in the case of BFS and DFS, we consider only depth or breadth, but in here, cost is important. In order to achieve this objective, UCS uses a priority queue, right? This priority queue, or you can say heap queue, is always giving priority to the nodes with the lowest cumulative cost so far. So far means from initial state to the current state. This ensures that the algorithm systematically expands the most cost-effective path. The interesting point here is if every edge has the same cost, UCS behaves just like a breadth-first search. But in general, it is more powerful because it guarantees the optimal path in graph where cost is different. That's why UCS is widely applied in scenarios where finding the optimal or least cost solution is critical. So here we see a UCS example. The main strategy here is to expand the cheapest node first based on the cumulative path cost. This is why UCS uses a priority queue. And in here, nodes with the lowest cost are given the highest priority. So in here, you can see we have this graph, and we want to start from source to the goal, destination, right? So in here, we can see this is called as cost contours. This contour represents the expanding frontier of nodes at increasing cost levels. As UCS progress, the UCS expands nodes layer by layer. So for example, layer number 1, layer number 2, layer number 3, but not strictly by depth. It expands according to the cost efficiency. Again, lowest cumulative cost. There is one misunderstanding here about the word of uniform. So uniform cost search, it doesn't mean that the cost of each edge is uniform, is the same, because the edges clearly have different costs. The key point is that the word of uniform here does not refer to the edge weight themselves, but rather to the search strategy, because UCS expands the frontier uniformly in terms of path cost. In other words, it explores nodes in their order of their cumulative cost from the starting node, not from the immediate. So, and it is different by the DFS, BFS, or by heuristic like ASR algorithm that we will study in the next lecture. The search grows outward in cost layers, and this gives every node the same opportunity to be expanded when its cumulative cost is the lowest available. So the word uniform in uniform cost search reflects that the algorithm treats path cost as the single uniform measure of priority, and in this way it can ensure optimality. So let's see one example to better understand how UCS works. We already learned that UCS finds the goal by expanding the node with the lowest cumulative path cost from the node S. From the node S to G, right? So the UCS prioritize paths that are cheaper, not necessarily those that are shorter in terms of the number of nodes. So in here, I told you that we use a priority queue, and this queue is used to keep track of the nodes to visit. We order them by the total path cost. It explores the graph step by step and expands one node at a time until it reaches the goal state. So here we see how it works. So at the beginning, when we are in level 0, our queue is something like this, S and 0, right? So we go from S, we start from S. So we pop the S from the queue and we will expand it, right? So S is out, then we expand it. Then we have this, our queue will be something like this, the children that we have A and 1, and also we have B and 4, right? This is our queue, right? This has been removed from the queue. So we pop the lowest cost node, that is A and 1, and we will expand it. So because here we have two children, C and D, right? So we will go like this, we calculate the cumulative path. So S to A is equal to 1, right? It's equal to 1, we can write like this, plus, and this one is A to C is 3, right? 3 from A to C. So it will be 4 in total. Then for the D, we write like this, 1 is to A plus 2 from A to D, right? So it is 3. So we can rewrite our Q like this. Q is D with cumulative cost of 3, and we already have B in our Q, right? We will write the B here, B in 4, and then C with the cumulative cost of 4, right? 4. So which one to remove? This one, right? D is removed. And we will expand the D, right? A, D, we already calculated is AD as 3, right? And D to F, suppose this one is 3, D to F plus 3 as D to F, then it is totally 6. The other path is SA D with the cost of 3 and D to G plus 3 D to G, right? This is totally 6. So because a goal node G is found here, we already know that G is our destination, right? We found, but the algorithm does not stop yet. It continues to search for a cheaper path to the goal. So our Q will be something like B4 that we have already, B4, then C4, then F6, and G6. The algorithm thinks that maybe there still exists a cheapest path, even though it has been found, right? So from here, we can pop. So B is 4, C is also 4. So we randomly select here B4. So B will be popped and it will be expand, right? So I will write it here. S to B is the cost of 4, and B to G is the cost of 5. So it is 9. So we will update our Q. We already have C and 4 here. So Q will be C and 4, then F and 6, then G and 6, then G and 9. So you can see still the path that we found from here is not cheapest, right? More expensive. So we will pop this one, C, right? So we will check C path also. So from C, we can go to E, right? So we can write like this, from S to A to C is cost of 4, plus C to E. C to E is 5, C to E is 5, so total is 9. So we will update our Q. Q is equal to F and 6, G and 6, G and 9, and E and 9. So among them, we pop the lowest cost, that is F and 6, right? F and 6. Then we will continue to check whether there is one cheapest path or not, right? So from F, we cannot go anywhere. It has no children here, so nothing to add here. So it will be removed. And we have G6, G9, and E9. We pop the lowest at G of cost 6, right? Since it is the goal, the algorithm stop here and find this one G as the goal. So the algorithm found that S to A to D to G is the optimal path with the cost of 6. This is the optimal path because it was the lowest cost goal node found in the priority queue. In uniform cost search, the algorithm expands all nodes whose path cost is less than the cost of the cheapest solution found so far. So if the optimal solution has a cost of, for example, C star, and every action has a minimum cost of epsilon, then the effective path of the search is approximately C star divided by epsilon. This means the time complexity of UCS is BO of B in power of C star divided by epsilon. This grows exponentially with this effective depth. In terms of memory, the fringe primarily holds nodes at the last level, so the space complexity is also BO of B C star divided by epsilon. Regarding the completeness, UCS is complete as long as the best solution has a finite cost and all actions have the positive minimum cost. And finally, UCS is guaranteed to be optimal because it always expands the lowest cost node first, and in this way it ensures that the first solution it finds is the one with minimal cumulative cost. Uniform cost search has the clear advantage of being optimal because at each step it always chooses the path with the lowest cumulative cost. This characteristic of UCS ensures that the first solution found is guaranteed to be the least costly. However, UCS also has some disadvantage. UCS focuses on the path cost and does not consider the number of steps it's involved. So as a result, in certain areas, for example, when there are cycles or zero cost loops, the algorithm can potentially get stuck or explore unnecessarily long paths, and this may lead to inefficiency or even an infinite loop. Alright, so in conclusion, UCS is considered as a powerful algorithm for finding the least cost path in a weighted graph or tree. By expanding nodes based on cumulative path cost rather than depth or number of steps, UCS guarantees an optimal solution. However, UCS focuses on path cost that can lead to high memory usage and also potentially infinite loops in graphs with zero cost cycles. In general, UCS is ideal when path cost matters more than the search efficiency. How? By combining reliability with systematic exploration. Thank you very much for your attention and see you in the next lecture.